Greetings everybody. Let's take a look at our first video on vector line integrals. And so before we really get into a vector line integral, we need to introduce the concept that, again, we're going to be seeing much later. It's going to be kind of a big part of the course from now on. But where we're talking about vector fields. And so just to define those, if we take a subset of the xy plane, so a subset of R2, then a vector field is just a function from R being a domain into R2 that we're basically going to attach a vector to every single point in our subset R. So if we've got our set R here that's kind of displayed, we take a point P in there, and that P, and then the vector that we're going to attach to that is our function f of P, so f of xy at that particular point, and it'll be x as a function of x and y, and the second coordinate will also be a function of x and y. Now, there's nothing wrong with absolutely having this in 3 dimensions as well, and so if we take a subset of R3, we can have a 3-dimensional vector field where for each point in our space, in our point in 3-dimensional space, we're going to attach a vector f of p to that one, and those components will be, the first component will be a function of our coordinates, the second function will be a function of our coordinates, and our third function will be a function of our coordinates. And so we can really visualize this as attaching, again, some vector to every single point in our 3-dimensional space. And those guys are really just called vector fields. Now, the work done by a vector field f along a particular path, we can define that as a line integral over the curve of f dot dr, where c is just going to be our curve, dr is really just going to be our tangent vector, or our tangent form, where it's just dr dt times our dt. Other forms that these things might take, if our vector field f looks like component functions p, q, and r is our position x, y, z, then dr just becomes our differentials dx, dy, dz, and so our f dot dr might have the form p dx plus q dy plus r dz, and so our arc length, our line integral over c of f dot dr then takes the form a line integral of p dx plus q dy plus r dz. So now let's compute an example of what that might look like. So if we do f dot dr, where f is going to be a vector field of the form x times z in the I direction and minus y in the k direction. So our c, so the curve that we're actually going to use is going to be the line segment that starts from -1, 2, 0 and goes to the point 3, 1, 1. Okay. So the first thing that we need to do is to come up with a parameterization for this curve. So one way that we can do that, since we're just parameterizing a straight line, then we can kind of use this quick and dirty parameterization of 1 minus t times where we want to end, plus t times the vector where we want to begin, with t just going from 0 to 1. So if we do that, kind of simplify things just a little bit, then we get a parameterization of 4t minus 1, 2 minus t, and t, with t going from 0 to 1. Looking at our tangent vector for that one, we just have dr being 4, -1, 1 dt. And the vector field, if we kind of restrict that vector field to the line integral, then we're just taking our component functions x, z, 0, and minus y, and plugging in the values that we had for our parameterization. X was going to be 4t minus 1, y was going to be 2 minus t, and z is going to be t, so that we get 4t minus 1 times t, 0, and then y was just going to be, so minus y just becomes minus 2 minus t. If we simplify all that, we get an expression like what we have down here. So then if we then go through and do f dot dr, well, that's just doing the dot product. We multiply 4 times 4t squared minus t plus -1 times 0 plus 1 times t minus 2 gives us this expression, which simplifies down to 16t squared minus 3t minus 2 dt. Now our integral over our curve C of f dot dr just becomes the integral from 0 up to 1, because that was the domain for our parameterization of f dot dr. Simplifies to 16t squared minus 3t minus 2. We do the integration, and we come up with an answer of 11/6. Kind of looking at our other form, what would one of those look like? Well, if we were given the line integral over C of xy dx plus xy dy plus dz, for our curve now they actually give us the parameterization as t squared and 1 minus t, with t squared going from 0 up to 1. So if x is going to be t, then dx looks like dx dt dt. So this is just our differential from Calc 1. So dx dt dt just gives us a 1 dt. Y is equal to t squared. Our differential dy just becomes 2t dt. Z becoming 1 minus t squared, our differential dz just becomes a minus 2t dt. So now we just take all of those expressions. We know what x is from our parameterization. We know what y is from our parameterization. We know what z is from our parameterization. We just computed what dx, dy, and dz are. So we just take all of those things, substitute them into this integral, so that we get t times t squared dt plus t times t squared times 2t dt, and then plus a minus 2t dt. Put all of those together, and that will simplify down to the integral from 0 to 1 of t cubed plus 2t to the 4th minus 2t dt. Evaluating that one just in turn gives us -7/20. And so for this one, we kind of have gone over a bit of an introduction to vector line integrals. So we've got kind of two different forms from that. We've got our f dot dr, and then we've got kind of our expanded form of some function dx, so p dx, q dy, and r dz, and kind of how to evaluate those. We'll continue with these in the next video, and I will see you guys